time to move to the next talk. So thanks again, Professor Tanaka. And now we'll move to the next talk by the Professor Masato Takeuchi from Osaka Prefecture University. His talk title today is Investigation on the Reaction Mechanism for Dehydration of Magnesium Hydroxide and Hydration of Magnesium Oxide by NIR spectroscopy. So please.
Professor Morita, thank you for your introduction. And Professor Chenkova, congratulations for your retirement and continue your research in Kobe University. And also, I would like to appreciate the organizing committee, especially Elena, for your support. My name is Masato Takeuchi. This is the title of my talk. Global warming and climate change due to the escalating carbon dioxide emission are serious environmental issues in recent years. To tackle these challenges, researchers have focused on the efficient and economical use of unharnessed thermal energy by using chemical heat pump system. CHP materials store unharnessed thermal energy by chemical reactions involving water, carbon dioxide, ammonia, and so on. Then the CHP materials are transported if needed and applied as a heat source. Most of Japanese knew this system. On the bottom of container, there are calcium oxide and water. By mixing these chemicals, we can enjoy hot lunchbox without any electricity. In this reaction, calcium oxide is a heat storage material and water is a heat carrier. This is a simple explanation of CHP materials. And now we are focusing on this reversible reaction, dehydration of magnesium hydroxide and hydration of magnesium oxide. This slide shows the NIR spectroscopy and the FTIR spectroscopy in middle IR regions. Maybe I don't need to explain the details of NIR spectroscopy. Anyway, the NIR spectroscopy was first applied to measure water content in grains in 1960s. Since then, NIR spectroscopy have widely been applied in many research fields: agriculture, astronomy, food chemistry, medical science, and so on. But so many in surface science field, especially in catalysis field. So we have reported some results on water, ammonia, hydrogen as solved on various catalyst surfaces. In this study, I will talk about the mechanism of magnesium hydroxide dehydration and magnesium oxide hydration were investigated by NIR spectroscopy, especially the behavior of the hydroxyl groups of the material surfaces involving phase transition was discussed. This is the experimental procedures. Magnesium hydroxide was purchased from a company. Magnesium oxide was prepared by a calcination of magnesium hydroxide at 600 degrees C. NIR measurements were carried out in a diffuse reflectance mode by using this FT-NIR system. And some other measurement conditions were shown here. Okay, so now I will show the results. This is a NIR spectra and X-ray diffraction patterns for the dehydration of magnesium hydroxide. Before heat treatment, you can see 3 different absorption bands here. First, I will discuss about these absorption bands. This is the same spectrum in the previous slide, and this is the FTIR spectra in middle IR region, observed at the same time. These 3 absorption bands correspond to absorption band here. So now I can say roughly former 2 bands can be assigned to less hydrogen bonded hydroxyl groups. And this one can be related to the hydrogen bonded hydroxyl groups of magnesium hydroxide. Then I will show the structure models of magnesium hydroxide. Magnesium hydroxide has a layer structure like this. And each layer interact with each other by hydrogen bonding. So interlayer OH groups here can be a hydrogen bonded hydroxyl groups. And when we focused on the surface, this OHC, C means corner, interact with 1 Mg2 plus cations, a cation. And OHE, E means H, interact with 2 cations. And OHT, T means terrace, interact with 3 cations. So we can say the absorption band at 7,339 wave number is OHE and OHC. And 7,300 wave numbers can be assigned to OHT. And this one is the interlayer OH groups of the magnesium hydroxide. But I think you are confusing on these complicated structure models of magnesium hydroxide. So just simply imagine like this. This is a photograph of milk crepe. 1 crepe sheet is the MgOH2 layer. And OHE and OHC are located here. And OHT is here. And interlayer OH groups are located in the cream part. By the way, I will go back to the spectral changes. As the temperature increased, these 2 bands combined to become 1 band here. And interlayer OH groups gradually decreased and disappeared at 450 degrees C. When we look at the XRD patterns, MgO phase was observed at around 350 to 400 degrees C. So these spectral changes can be related to the phase transition of magnesium hydroxide to magnesium oxide. For further discussion, I will show the second derivative spectra as you can see here, as the temperature increased, each component due to the magnesium hydroxide gradually shifted to lower wave number regions. This behavior means the distortion of magnesium hydroxide frameworks. It means that hydrogen bond networks becomes dense. Then I will show the NIR spectra and XRD patterns for the hydration process of magnesium oxide. Before hydration, we could find one band here, 7,360 wave numbers. This absorption band can be assigned to the isolated hydroxyl groups of the MgO surface. After hydration for 10 minutes, this band changed to here. This band can be assigned to the hydrogen bonded hydroxyl groups of the MgO surface. And after 30 minutes, we could find a small band here. This band can be assigned to the interlayer OH groups of magnesium hydroxide. And increasing the hydration time, this band increase. And after 4-hour hydration, we could find typical 2 bands here due to the magnesium hydroxide. And also we could find MgO phase by X-ray diffraction patterns after 1 hour hydration here. So this spectral changes also corresponded to the phase transition from magnesium oxide to magnesium hydroxide. And this is the second derivative spectra during the hydration process of magnesium oxide. In the formation of magnesium hydroxide during the hydration process, each component due to the magnesium hydroxide did not shift toward the lower wave number regions. This result indicated the magnesium hydroxide framework was not distorted during the hydration process of magnesium oxide. And this figure shows the time course of the absorption intensities. In the formation process of magnesium hydroxide, interlayer OH increase, and also OH edge and corner increase, but OH terrace decreased. This behavior is quite important because it suggests the stacking of MgOH2 layer. I mean, in case of monolayer, both sides can be OH terrace, but when several MgOH2 seats are stacked, OH terrace interact with each other to form interlayer OH groups. So finally, I will show the proposed mechanism of hydration of magnesium oxide. Before hydration, isolated hydroxyl groups are located on the MgO surface. And these isolated OH groups easily hydrated to form hydrogen bonded OH groups like this. Then small MgOH2 sheets are formed and totally covers on the surface, MgO surface, like a patchwork. Then MgOH2 sheets are stacked to form multi-layer. So this is the conclusion of my talk. Dehydration of magnesium hydroxide and hydration of magnesium oxide were observed by NIR spectroscopy. 3 different hydroxyl groups of magnesium hydroxide and 2 different hydroxyl groups of MgO surface could be assigned. NIR spectroscopy could detect the structure changes of magnesium oxide surface into magnesium hydroxide, which cannot be observed by X-ray diffraction measurements. Maybe I have 2 more minutes. I want to introduce one more result. Can I?
Yes, please.
よいしょ、あれ。よいしょ。Just a simple example. よいしょ。This is an NIR spectra of water absorbed on molecular sieve zeolite. You can see here and here. The water molecules immediately adsorbed on the zeolite surface, especially inside the pore. And this band increased to 5,200 wave numbers. This is a water molecules close to a liquid phase. And this is the behavior of water adsorbed on the zeolite. This tendency is quite important. The ratio of peak intensities S0 per S1, S2, Sn decrease to become about 0.3, which is close to bulk water. And this is a brief introduction of results. Okay, thank you for listening.
Thank you very much, Professor Takeuchi. So now open for the question discussion. Any question, comment?
Yeah, I really have a comment. Can I just? I wrote I have a comment.
Okay, thank you.
As always, beautiful work, beautiful work. I mean, it's so precise always. Just I calculated the overtone. I mean, in the first overtone, we have published a paper. Dusan Kozic and Professor in Swiss group at KO. They published a paper on dehydration, and the bands are exactly what you said. So I calculated them. So there are 7157 is so-called trapped water. We call it trapped water because it is within ions. Single, this one? Yeah, this one. It's single. I say free but not free water molecules. So the band is 1392 to 57 depending on the ions. Thank you, Elena. Yes, exactly. And in the other one, 1362, 7339, 7306. This is so-called water solvation shell, which is a kind of hydrogen bonded two layers of water molecules. So what you described is absolutely consistent with what we found in other systems. So thank you. That really is so beautiful. It is the only word I can say. Thank you.
In fact, today I don't discuss about the absorption of water, especially the structure changes of the material. Maybe we could find the absorption and the first process of the interaction of water and magnesium oxide or magnesium hydroxide. I will try such kind of experiment. Thank you for your comments.
Okay, Elena,
thank you, Professor Marta. Takeuchi Sensei, this is such a beautiful work. I really have no words to describe, but I have just one question, because what you did for hydration of this magnesium dioxide, the hydration of first layer, this is something that can be related to any other material, that kind of hydration structure. So I wanted to ask, because in other materials, we have what you just last said, we have other, when this process of adsorption just begins, or process of evaporation just begins, we have some water bands around. So when I recalculate, that would be 6,872 centimeters to -1. Do you have something like that? Did you encounter maybe that kind of water? Because I don't have, I call it undecided. So it is around 6,870 centimeters to -1. That's the
yes. In case of magnesium hydroxide, there are no crystallization water in the material. But if we measure the calcium, magnesium carbonate, maybe this one is better. Yes. This is the NIR spectra of magnesium carbonate and magnesium hydroxide. In this case, there is a crystallization water. This material contains crystallization water. So we can observe this band here. I think, but this material does not have surface hydroxyl groups here, because carbonate species totally covered on the surface.
I see. Thank you. You answered a few actually questions with this. I didn't do that. Thank you very much.
Thank you.
Thank you very much, Professor Takeuchi. So let's move to the next talk.
Okay, thank you very much.